everyone, and thank you for joining this rendition of the KITP NSBP Innovate seminar. Today we have uh, Christopher Ayala, and he will be speaking to us about high harmonic generation and wide gap semiconductors. I will give a brief introduction on Christopher, and we will have 15 minutes at the end of this rendition to have questions. So Christopher Ayala is a PhD candidate in applied physics at the University of Michigan, specializing in ultrafast laser systems and high harmonic generation and wide bandgap semiconductors. His research combines the design and optimization of femtosecond laser sources with advanced spectroscopic techniques to study light-matter interactions. He has held research positions at NEC Laboratories America, ENS Paris-Saclay, and the University of Witwatersrand, where he developed expertise in fiber optic sensing, fluorescence lifetime imaging, and quantum ghost imaging with machine learning. He earned his BS in physics and applied mathematics and statistics from SUNY Stony Brook and his MS in applied physics from the University of Michigan. Beyond the lab, he's an active leader and mentor, having served as president of the graduate chapter of the Society of Hispanic Professional Engineers and helped in creation and served as president of the National Society of Black Physicists Willie Hobbs Moore chapter at University of Michigan. His long-term goal is to bridge advanced optical technologies with real-world applications in communications, sensing, and next-generation photonics. So, Christopher, take it away.
To begin, thank you for the invitation for today's talk. It's quite an honor, and I'm always glad to be able to share the research with other people who are interested. I am a seventh year graduate student and PhD candidate at the University of Michigan, and I work in the Comparative laboratory. And today's work that I'll be talking to you guys about will be high harmonic generation in wide gap semiconductors. So the overall talk will be a little bit of background on all those words that I just said, high harmonic generation in wide gap semiconductors, give you guys a little bit of background to understand what I'm saying, the methodology on producing these high harmonics, some clean results that we were able to achieve in the past few weeks, as well as the overall conclusion that we've made from this work so far. So to start off, what is a high harmonic generation? So high harmonics can be formed from both a gas and a solid material. You take an intense laser pulse of some sort, you impinge it on a target material, and once these two interact together, high harmonics are generated. So the first observation of harmonics were generated in gases such as xenon and argon in the late 80s. And it wasn't until the seminal paper in 2011 where Professor Gamir studied zinc oxide, and that had opened the floodgate for various different solid materials to be studied as well, such as silicon oxide, magnesium oxide, as well as graphene. A little backstory, though, is that the first instance of harmonic generation was actually observed at the University of Michigan. Professors Peter Franken, Gabriel Weinreich, Wilbur Peters, as well as Alan Hill were the first to observe what's known as second harmonic generation. How this process worked is that Professor Gabriel Weinreich actually suggested the researchers to swap the material to quartz because this was a broken inversion symmetric object, which means that whichever way you turn it, it will not look the same in both directions. They were able to take a ruby laser at about 700 nanometers, interact it with the target medium, in this case, the quartz, and produce second harmonic generation at double the original frequency of the incoming light at 347 nanometers. What we have shown here is called the polarization equation, and this polarization equation just helps describe how a medium responds to an applied electric field. When you think about harmonic generation, we can describe this as a perturbative regime or a weak field, and it's characterized by a rapidly decreasing efficiency with increasing harmonic order, which means that the chi3 effects, chi4 effects, and so on are not taken into account because they are so weak in this case. That's why we see a second order effect. It isn't about until 20 or 30 years later that the first instance of high harmonic generation is observed. And the main difference that you'll note is that after the ninth harmonic, instead of that decreasing efficiency that I had just mentioned, that there's actually a plateau and then it rises again, and we see another increase in harmonic order. This actually shows that we are now in the non-perturbative regime and must now consider those higher order terms to take into account. You may be wondering why you only see the odd order harmonics shown, 9, 11, 13, so on and so forth. This is because that atomic vapors have inversion symmetry. This means that because of the geometry, all the even order harmonics in this material are actually canceled out and we only see the odd orders produced. So why do we care about high harmonic generation and these ultra-fast pulses of light? Well, it was in 2023 that attosecond science and the generation of high harmonics actually received the Nobel Prize. These pulses of light, which are at 10 to the negative 18 seconds, help us describe things that move on that ultra-fast timescale. One example for you is that electrons are moving at attosecond timescale. DNA is doing all these different processes at attosecond timescales. And to get an understanding of how these processes work, you need something equally as fast or faster to study these dynamics. Another benefit of these attosecond pulses is that you're able to generate tabletop soft X-rays from the gas phase and extreme ultraviolet pulses from their solid state counterpart. And as I mentioned earlier, you can now use these ultrafast pulses to probe driven ultrafast dynamics. To get a theoretical understanding of how these harmonics are generated within the system, we have to take a look at what's called the three-step model. The three-step model is an interpretation of how these intense laser fields and matter interact to produce said harmonics. And it can be broken down into ionization, propagation, as well as recombination. When you look at one thing to keep in mind before I move forward is that this process of generating harmonics happens every half laser cycle, so 2 within 1 period. So within the ionization phase, a high strength electric field is a high electric field interacts and an electron is tunnels out of the system. In our case, the strong electric field is our laser. So now you can imagine that as this electron is traveling further and further away from the system, and as the field is switching direction, this electron is now accelerating and picking up energy as it returns back towards the center. And then if this electron is reabsorbed, the high energy photon is emitted in this case. It's important to note that the probability of whether or not this recombination occurs is due to several factors, including the duration of the field, the initial energy, and some other factors. Here is a combined picture of the 3 phases of the tunneling ionization, the propagation, as well as the recombination of the electron. You can think, another way to think of the ionization is that this electron is tunneling through the potential barrier that's lowered by the strong electric field and then is freed with approximately 0 kinetic energy, and it leaves this localized hole. And it's also important to note that it has that ionization energy, I of P. As this electron is then picking up, accelerating and picking up momentum, we have it as a maximum kinetic energy that can be picked up is 3.17 times its maximum energy. So when you look at said recombination, this electron is now transferring its ponder mode of energy plus the atomic ionization potential that it had in the beginning into this emitted high harmonic photon. One thing to keep in mind that I might have glazed over earlier is that another reason you'll only see odd order harmonics in this case is that there is an interference between the emissions at each half laser cycle. And in the case where the harmonic radiation is at successive half cycles, they have opposite phase. And because of this, it allows the odd multiples to constructively interfere, where the even multiples will destructively interfere, and then that's why we only see odd order harmonics. So that was all for how gases are thought of to generate harmonics. And now we want to take that same mindset and bring it into solid harmonics. One thing to note of difference, obviously, is that in a gas harmonic, there is a low density, so less interaction or attraction with other atoms in its vicinity. Whereas now within solids, the typical spacing tends to be about 0.5 nanometer, and there's a definite higher volume of density of atoms. So now you have to take into account how these atoms and harmonics interact with other atoms around it. And to do so, we will use something called band theory. So band theory allows us to look at this whole array of atoms as just modified single electrons. So instead of these discrete energy levels that we know and love in the free atom, we now have what's called these energy bands. So the main difference between, one thing to note is that the valence band is described as this highest band energy containing electrons and is full, and the conduction band just happens to be the next band, which is not full. The difference between an insulator and a conductor, which you guys know, is that there is a required amount of energy to bridge the gap between the valence band and conduction band, and that's called an energy gap. Conductors allow for a free flow of electrons, and an insulator has such a large gap that it is hard to bridge normally. We're going to be looking at a special material that combines both of these effects, known as a semiconductor material. The semiconductor has a small enough gap that can be bridged either by some thermal or some other excitation to help bridge the gap between the two. And in our case, it is that laser that I keep referring to. So when we think about harmonics in solids, we have to keep in mind that we're now looking at everything in K or momentum space, because this allows us to assume that these band gaps are parabolic due to it being similar to a free particle. So how does single photon absorption work? This absorption really only works if the energy of the photon used is at least as large as the band gap. And when an electron is excited from this valence into the conduction band, it leaves behind a hole. Note that this hole can form anywhere between the valence and the conduction band, here, for example, as well as out here. It's just most energetically favorable for the direct gap between the valence and the conduction band. What's neat is that if you start taking into account the Coulomb interaction between the hole and the electron, we may see what's called an exciton, which is a bound electron-hole pair that forms near the band edge or band gap. So in the case where the band gap of the material might be larger than the incoming energy of the photon, you will need something called multi-photon absorption. And in this case, that just means that if the energy that you have is not enough to bridge the gap, you just need to use multiple photons of the same energy to then sum and bridge that energy gap. The right image here is a representation of position versus energy with the valence band and the conduction band here. And what happens when you turn on a laser field, you see that the valence band and conduction band have an easier way to model the tunneling that we have seen in the gas phase three-step model. So the main difference between a gas phase high harmonic and a solid harmonic is not quite too different. You see here that the tunneling and ionization is represented by step 1 here, with the electron being pulled into the conduction band and having a whole pair. In step 2, you have your propagation of your electron, and in step 3, you have here your recombination back into the valence band. In the case of harmonics in solids, there are actually 2 generations of harmonics that are known. The first being intraband emission. This is caused when the electron is sloshing around in the conduction band and helps emit some sort of harmonic radiation. And then the one we all know and love, the recombination process, in which the electron combines back with its hole, and this produces what's called interband emission. Here is a nice physical picture to give you a better understanding of what's happening, in that you have an electron in a hole that is born. As these two are propagating away from each other, it starts emitting some sort of high energy photons, and that when it recombines back together, it also produces these other higher order harmonics. So to give a quick summary of what the differences are, is that even though high harmonic in gases allow for higher cutoff energies and higher order harmonics, to do so you need very, very high vacuum, as well as scalably higher laser intensities relative to what you can do with solids. For example, solids can generate harmonics up into the UV range, which is lower than the X-ray range, but we're able to do so within ambient conditions, and we're able to change and determine different material growth and material observations with solid harmonic generation. The other thing to note is that the laser intensities are about 2 to 3 orders of magnitude less, and allows you to scale and have compact systems relative to gas phase harmonics. So what am I doing that's different than the current experiments studied? So we're going to be talking about wide-gap semiconductors. Traditional examples of semiconductor materials that you guys know and that might be in your phone and in your everyday lives and cars and whatnot are gallium arsenide and silicon. These traditional semiconductor materials are categorized as materials with a band gap anywhere between 0.6 and about 1.5 eV. What I describe as wide-gap semiconductor materials are the technologically next step components, gallium nitride, as well as silicon carbide. The main difference between these two is the band gap. As you can see here, most of these materials will have a band gap of greater than 2 eV. What does this increased band gap allow us to do? Well, these materials can now withstand higher electric fields. They are able to generate higher harmonics in more efficient ways, because you're allowed to grow the material in whatever format you would like, which you'll see on the next slide. And these devices are allowed to operate in harsher environments. And in that case, it's working at higher or lower temperatures than you normally would imagine. The 3 samples that I am studying currently are gallium nitride in bulk form, gallium nitride in epi-layer form, which just means that you have one sample grown and then you're able to deposit the gallium nitride in a very fine layer and grow it in a very in a way that minimizes defects. And the final sample is magnesium oxide, and we chose magnesium oxide as a control experiment control material that has been experimented heavily upon. As you may have noticed, both the gallium nitride samples are grown on what's called a sapphire substrate. So this is a real-life size to scale picture, and we study all of our harmonics in reflection geometry. So how do we do these harmonic generation measurements? To go back just a little bit, we had a collaboration experiment where the incoming laser was about 1950 nanometers with a repetition rate of about 1 kilohertz. What I mean by two-color system is that you take a BBO crystal, you have a fundamental of about 2 microns, and you interact it with a BBO crystal, which puts out the second harmonic generation at about 1% of the total output. When you interact the fundamental and the second harmonic generation pulses, you are actually breaking the inversion symmetry of the laser, and in so doing, you now have broken inversion symmetry in the system, and that allows you to have both even and odd order harmonics. The main to only have single color or only odd order harmonics, all you have to do is remove said BBO crystal, and you have a single color system again. With this two-color system, we were able to observe all generated harmonics from the third in the visible down to the seventh at near UV, with the harmonics being approximately 280 nanometers. What you may notice here is this really tall brown peak, and this is what I had referred to as earlier as the exciton, photoluminescence. And in this case, when the excitons are recombining, they are forming near the band energy, which is what you see here. And photoluminescence, in a sense, is just the incoherent emission of light. That's why it's alongside all the other orders of harmonics. If we take that same two-color system and turn it into a one-color system and send it into a high fidelity spectrometer, we're able to actually even see the ninth order harmonic sitting here at around 217 nanometers. What I have labeled here on the side as the forbidden zone just refers to vacuum ultraviolet. Vacuum ultraviolet refers to the point at which air starts absorbing light. So if you do not have a vacuum spectrometer or something, or all of your material is in vacuum, anything that's produced after under 200 nanometers, pretty much you wouldn't be able to see. So that was our stopgap and limit here in this experiment with a collaborator, and that has fueled us to be able to acquire a new laser with somewhat similar specs to what I had just described, but the main difference is that our center wavelength now sits a little bit higher, so that means the photon energy is just a little bit lower. The repetition rate is now going from 1 kilohertz to about 1,000 times that at 1 megahertz, and this gives us higher pulse energy per pulse. Our goal is to have as high of a peak energy as we can to focus onto the sample at one point so that we can generate higher order harmonics. So we take the output from this very nice new laser that we have here, and I give you guys a close-up of what our experimental setup looks like in ambient, keeping in mind that this whole experimental setup, it takes maybe a quarter of the space that a gas chamber and gas phase harmonic might produce for you. We have, importantly, an ND wheel, which allows us to attenuate and choose how much pulse energy we are putting onto the sample. We have an OAP, an off-angle paraboloid mirror, to focus it tightly onto the sample, and the sample just gets sent through a lens to focus onto our spectrometer. So we'll first talk about this gallium nitride bulk. So as you can see here, we're able to reproduce the results and see the third order harmonic, the fifth order harmonic at 400 nanometers, this excitonic response for the gallium nitride, which is at about 365 nanometers, and a seventh order harmonic at 286. To take into account, I was not able to fully see into the lower end of the UV spectrum, and this is most likely the case due to our device limitations that we have here. So what I'm allowed to do with this spectrometer is I have a X, Y, and Z control, and I'm allowed, I can take this spectrometer, move it around, and do what's called optimization of our harmonics. This optimization is specifically targeting a single harmonic peak and trying to increase its intensity and power relative to itself versus the other order harmonics around it. I don't have a good representation of a power chart, but if you take the area under the peak and do it for multiple different power levels, you should see that as the power increases, it should scale to the polarization to the third, P to the third, or the power to the third. You would see this occur in both the third and fifth harmonics, that they follow a trend of I to the 3 and I to the 5 for each harmonic order. So each harmonic order should follow its power trend. Third harmonic should follow I to the third, fifth harmonic should follow I to the fifth, so on and so forth. What you actually see happen is that during this exciton optimization, or when I look at the exciton, that it would follow the I to the 3.5, if I'm not mistaken. I didn't include it here, I apologize. But you would actually see that it's about 3.4 or I to the 3.5. And that just means that you can confirm that it takes about 3 or 4 photons to bridge the gap for this material, for the energy gap. I don't have it placed here, but what you would see for the seventh order harmonic is that it would follow some power law, but then it would start tailing off as you increase the intensity, and that would show that the harmonics are now in a non-perturbative regime because it's not following the power law that you would expect. So we see here that even though it's not so obvious that there is a following of this I to the 3, but it deviates, or I to the 4th, but it deviates a little bit because of this being at the band gap. So when jumping into talking about the MgO template, nothing super special can be seen so far. It's just that we have a peak shown at the third harmonic, and we have the power law relation that should follow an I to the 3 power law. The issue is that we just haven't done any more experiments on the magnesium oxide yet, and all my efforts have been pretty much put towards looking at the gallium nitride and optimizing to see if I can even get that last ninth order harmonic before we play around with the other samples. So I say all of this to, and you guys might be wondering, why is this any different than what you and your collaborator did? Well, that is a good question. The main difference is such that we can now take part of this pulse, and instead of sending it into our ambient harmonic generation sequence, we have in my lab a vacuum chamber. This vacuum chamber, once we send the same intense light, focus it onto the sample, we now have a grading spectrometer with a very, very, very sensitive camera. This sensitive camera should be able to pick up harmonics that are generated within this forbidden zone that I had mentioned earlier because now that the sample is in this vacuum chamber and we pump it down, we should be able to generate harmonics that are into the vacuum ultraviolet range. So in conclusion, at least now we're able to fully develop a system that consistently generates up to the 7th harmonic. Hopefully we can get it to further push it further. I've demonstrated a compact and reliable approach to generate these high harmonics, and we have showcased the potential for a scalable and sustainable harmonic generation. The next steps that we aim to achieve, hopefully soon, is to extend these higher order harmonics to the 11th, 13th, and so on, which would be wavelengths that are under 200 nanometers in the vacuum ultraviolet, and hopefully address our current limitations, being the efficiency. There are material damages in the gallium nitride, which is why I didn't show it, the gallium nitride bilayer or the epi layer, and there are some phase matching properties that aren't as important, but can be helped to achieve less limitations. I want to acknowledge my lab members here for being great and having great feedback on this PowerPoint. And I'd like to also thank the theorist, Dr. Makilo Kira, as well as the materials professor, Dr. Zeddy and me. Thank you for listening. And if there are any questions, please let me know.
Thanks so much, Christopher, for that. And Carlton will be able to moderate questions. So if you have any questions for Christopher, please go ahead.
Hello, yes. So yeah, we are currently in the Q&A portion of the talk. And so far we have one question. If you have any, feel free to use the Q&A feature through Zoom. But the first question comes from Denmark Elisma. I hope I'm pronouncing your name correctly. Where they ask if is the laser used for communication applications, and is the recombination mentioned in Augur 1? If not, what kind of recombination is this?
Thank you for the question. So in terms of communication, I believe this is more of a process in which we study new physics, and I think an example of what this would be used for might be something like creating a vacuum ultraviolet frequency comb to observe meteorology and different materials. I don't know if there's any communication applications linked with high harmonic generation. I would say the only thing I can think of would be that the next steps that people are trying to take with this harmonic generation is now to scale and compact it even more so than what I've already done. For example, I mentioned that your typical gas harmonics will take up a whole optical table. My harmonic generation process is scaled down to about maybe half of that size. And what you can do then is send that same light into optical fibers to guide and have many different order effects that are also requires less laser intensity as well. In terms of recombination being an Augur 1, I do not know what that means, if you wouldn't mind clarifying.
Denmark, you should be able to speak, it looks like.
Oh, okay. Yes. Can you hear me now?
Yes, I can.
Yeah. The quick question I was referring to Augur because that's actually what we find a lot in semiconductor applications, for semiconductors, and I just wanted to know if the concept is the same. The kind of recombination that you have is considered to be the same recombination that you see in semiconductor devices like transistors. If it's the same that you're actually seeing in your experiment, and that's what I wanted to know, what kind of recombination that you're seeing, or what kind of recombination you have.
I'm still trying to understand what you mean by different type of recombination, because
Recombination is basically when you have bandgap semiconductor, you actually have electrons going back and forth. Sometimes you generate photons, and it goes back to the device. I wanted to know if the recombination, if you generate a new hole, or if you have if you have the same electron hole that you started with. That's actually what I was referring to when I was asking about that kind of combination.
I understand I understand your question now. Thank you. So what's happening is that this process is creating many electron hole pairs, and it's only in the few cases where they recombine together that they are. So harmonics are always being generated because in the solid case there are two forms of these harmonics that are generated. It's just that the recombination happens more infrequently than for the intraband emission, but it doesn't have to be the exact same hole pair that was generated. As I stated earlier, this electron hole pair can form right here, it can form right next to it, it can form right here, and it's wherever it just relaxes back down to its valence band that it produces that harmonic. That specific recombination type of harmonic.
Okay, thank you.
Thank you for the question. We have a question from Alan, and then Layla, and then Dr. Roberson, and then Elizabeth. So Alan asks, does your lab do molecular beam epitaxy, or do you get samples for Zetchin?
Thank you for the question. Unfortunately, we are not the growers for the materials ourselves. The collaboration exists between one theorist, one material growth person, and me as the experimentalist. I definitely wanted to have the experience to grow these materials, but with our collaboration, there was no way to really justify it without it costing my professor a good amount of money that isn't really necessary. But yes, the second material that I'm studying, specifically the gallium nitride. Oh, other way. Right here. So this material, as I was mentioning earlier, is grown via material beam epitaxy, in that you have the sapphire substrate, the aluminum nitride is grown right on top of it, and then specifically the gallium nitride is deposited across the material in a way that allows you to have, like I said, that fine material deposition.
Okay, thanks so much.
Thank you. So the next question actually comes from Layla Smith. And they ask, what is one challenge you experienced during your experiment? And they want to thank you for giving an awesome presentation that was informative and insightful.
Well, thank you. So this experiment and all experiments always have some ups and downs. One of the most recent challenges that we have discovered is that the output of this beam doesn't seem to be it seems to be elliptical. So what that means is that the beam is wider in one direction than it is the other, and that the issue with that is when you are now looking at this focusing apparatus, the material wouldn't give you the highest peak intensity power onto the sample that we would hope to get. We're still able to clearly generate a third to seventh order harmonic with high intensity, but we're thinking currently that this could be a limitation in even seeing that ninth order harmonic, and it would be an issue when going into vacuum and other higher to just try to find higher order harmonics, because we would just not be able to produce the peak intensity of to generate harmonics. And one thing I didn't mention earlier, which this is a good place to do so, is that to generate harmonics, you need about 1 terawatt per centimeter squared focused onto the sample. And with what we have currently, we're sitting right above that minimum limit. So as whatever we can do to increase that maximum peak power onto the sample would be a great issue to fix, essentially.
Awesome. So we have 2 more questions. The first one comes from Dr. Roberson, and it's is it more important to have HHG wavelengths be present or for the HHG wavelengths to be relatively strong?
That's a good question. I think in our proof of concepts, our goal is to have harmonics that are visible in the sense that they exist. And I think what you do after is worry about the intensities of these harmonics. Because as I stated earlier, once you have them within the range of the spectrometer that you see, you can then take your input spectrometer and play around with the angularity of the light into the spectrometer. And at that point, you're increasing the intensity in that manner. I think the goal first is to be able to see the harmonics, and then once you have even seen a small peak of that harmonic, you can now hone in and increase that intensity and play with that specific harmonic after the fact.
Awesome. This is a great answer. So the next question comes from Elizabeth Ude, and they ask if you could give a little bit more light on why we need to do harmonic generation.
Yes, so that's a good question. One of the more recent materials that we study, like gallium nitride and all of these gallium nitride and these wider bandgap materials, we want to be able to characterize and study the effects of these materials before we first bring them into new technologies that I had mentioned earlier, that the effects are such that we can now increase the voltage and hit it with more before it gets damaged. And in that sense, having these materials be able to do these processes at higher damage thresholds is key for new technologies to be created. But on the physics side, the reason for harmonic generation that I do want to stress is the pulses that are generated from high harmonics under or near vacuum UV or at the extreme ultraviolet point. These attosecond pulses that are generated really allow you to study the dynamics of how electrons move, and to re-emphasize the fact that if you have something that moves really, really fast, it's nearly impossible to have a single frame catch what's happening in that moment. So you do need something ultra fast, and in this case, high harmonic generation produces these attosecond pulses to essentially use the produced beam of light and interact it with some DNA sample or a quantum dot, for example, to see how does this electron move within this sample? How does the DNA get affected after I interacted with this attosecond pulse? It's all about the pulse afterwards. And to study materials, a simplified way of studying materials is that you have a material with a known laser and you get a unknown pulse out, and you can just study the difference between the two. And now you're able to say, oh, I know all these things about this material by interacting it with a known light source that we have.
Another great answer. We're running a little bit short on time, I think. So I guess the final question would be from Dr. Roberson, where they ask, in regards to, I guess, the elliptical beam problem you mentioned earlier, if you could use a cylindrical lens to expand in one dimension to make the beam more circular and then focus it down to improve beam quality.
Yes, that is actually what my next goal is this week, in a sense. The main issue that we have is such that we don't have a camera to actually give us an accurate beam size. So we're still trying to finagle a way to measure the beam at different locations to get an accurate beam size measurement so that I can choose the correct cylindrical lens to then make it spherical again to then focus it down. So I'm at the stage right before committing to buy and committing to buy this cylindrical lens to help correct for the issue of the ellipticity. But that is a good point. Thank you.
With that being said, I guess the last thing the audience wants to say is to just thank you for your thoughtful responses and the talk in general. And yeah, I guess I'll hand it over to Alan to close us out.
Yes. Thanks so much, Christopher, for this talk. And thank you all in the audience for your wonderful questions. And we hope to see you again for another rendition of the KITP NSBP Innovate seminar series. So thank you and have a good afternoon.